Greetings, everyone. Welcome to KA Academy, lesson number 3, as we are embarking on the PLC knowledge. And as we have dealt with the first language in our quest to decoding the 5 languages that would be uh, uh, dealing with in terms of our journey of programming. I wanted us today to deal with the function block diagram, and then we can go back later on to do the practical task as is for the structured text. But today I wanted us to go through the function block diagram. Function block diagram in real form or in real life, it mostly translate the knowledge that we might have learned or encountered when we were dealing with uh, gates in digital electronics. As you can see here, this is what you call a derived function block, meaning as the way it looks based on observation, the way it looks, that means there are blocks behind this big block that you see here that are working at the background to do the logic that would give us act with these inputs that are here on this block. And then before we dive into this, let us just remind ourselves of the theoretical background in terms of uh, the gates. If you remember, in gates we have a buffer gate, which in most cases we just give whatever we receive as is. If we give a 0 here, it will come out as 0. If we give a 1, it will come out as 1. The inverse of it, we have what you call a converter or a NOT gate, which means if we give 1, it will come out as a 0. If we give a 0, it will come out as a 1. So we are inverting whatever that we got. And then second on the list, or third on the list, we would have an AND gate. AND gate meaning the characteristics. If we look in the truth table of an AND gate, if we put a 0 and a 0, we're gonna get a 0. Because this we normally call it a multiplying gate. So 0 times 0 is 0, and 0 times 1 is 0. 0 times 1 is 0, but 1 times 1 is 1. Then we'll get a 1. Then and then would be the inverse. That means it invents whatever that this one was doing, the result will be invented, meaning it is still a multiplying gate. So 0 times 0 is 0. That 0 is a 1. So 0 times 0 is 0, but not 0 is 1. And then 0 times 1 or 1 times 0 is 0, not 1. Not 0 is 1. 0 times 1 is 0, not 0 is 1. And then 1 times 1 is 1, not 1 is a 0. That's why the truth table looks like that. And then we're gonna move to an OR gate. OR gate, either or, uh, either A or B in this case. So if A is 0 and B is 0, we're gonna get a 0. But then if A is 1 and B is 0, we're gonna get 1, either or. So we're gonna receive the high signal, which is 1. And then if this one is 0, this one is 1, we're gonna get a 1. And then if they are both 1, we're gonna get a 1. So meaning we're gonna get a high signal. And a NOR gate, it's the inverse of that. So that means 0 or 1. I mean 0 or 0 is a 0, not 0 is 1. 1 or 0, 1. Not 1, 0. 0 or 1, 1. Not 1, 0. 1 or 1, 1. Not 1, 0. And then we go to an exclusive OR gate. Exclusive OR gate, this gate looks for inequalities within A and B. If they are not equal, it's going to give a high signal. But if they're equal, it's going to give a 0 signal. So 0 and 0, they means they're equal. So we're going to get a what? A 0.